So I called this lesson a little bit about lightning. I'm not going to be specifically asking you about lightning on your test, but Nick, a lot of the concepts here are good basic reviews of some of the concepts you'll see on your electrostatics test. And so here's the first question. It says this. Example 1, explain why an atom will be ionized, the electron will be ripped off of the atom, if it's placed inside a sufficiently large electric field. That's a good question. So, first of all, what direction is the electric field in this picture? To the right? Which way will the electron feel a force then? Okay, to the left, because we had to define an electric field somehow. We defined it in terms of positive charges. Its direction is the direction the positive charge would feel. There's a few questions on the ultimate review, for example, where it tells you the force that an electron feels, and it asks you what's the direction of the electric field. Whatever the opposite direction is of the force that the electron feels, that's which way a positive would feel a force. That's the direction of the electric field. So if the electric field is pointing right, the electron will feel a force to the left. I'll call that Fe for force, electrostatic force. If you get a big enough electric field, a large E field can apply a big enough force to remove an electron. The protons are pretty locked into the nucleus, although they will feel a force in the opposite direction as well. So the nucleus will feel a force in one direction, the electron will feel a force in another direction, and if you bump the electric field up big enough, you can get a big enough force. How is that possible? Well, on your formula sheet you have this. Electric field is force divided by charge. Lena, how would I get the F by itself? How would I move the Q over? So basically, if I bump this electric field up enough, it will apply a force on the electron. It's an electron, 1.6 times 10 to negative 19, big enough that whatever force it's being held onto the nucleus by, the electric force, the external force, is larger. We call that ionizing. You've learned in chemistry that an ion is when a charge has lost at least one electron in its outer shell, when an element has lost at least one electron in its outer shell. Okay? It turns out that for air, which is a mixture mostly of nitrogen and oxygen and other trace gases, it takes about 3 million volts per meter to produce ionization. 3 million volts per meter is 3 times 10 to the 6th, and that's also newtons per coulomb. That's the magnitude of the electric field. I happen, because I'm a nerd, to have memorized this figure. Remember when we were doing the Van de Graaff generator, and I was estimating how long the sparks that we were generating was when people were giving each other shocks, and I was able to roughly calculate the voltage. Basically, I took that 3 million, and I divided it by 100 centimeters, 1 meter, and I said every centimeter is roughly 30,000 volts, roughly. There's a bunch of other factors, humidity, temperature, but very roughly, every centimeter a spark jumps in air is about 30,000 volts-ish. So that's how I was able to say, I can't remember who was all getting shocked. Oh, that was about 4 centimeters. That's about roughly 120,000 volts, 125,000, depending on how accurate you want to be. This 3 million volts per meter, newtons per coulomb, it might seem like a lot. Zane, it happens all the time. It happens in the crackle you hear when you pull apart clothing that comes out of the clothes dryer on a dry day. You might occasionally hear some static, especially if you haven't put in some kind of a fabric softener or something to get rid of the static. Depends on the fabric there as well. I have a couple of shirts that come out and they're always crazy staticky. It's also in the shock that we get when we walk across a carpet on a cold winter day and then reach for a doorknob. I moved into a new condo in March. I moved out to Abbotsford. I don't know what it is about my hallway and my door. Every time I reach my key for the lock, there's always a spark every time. So I'm building up enough of a charge that there's enough of an electric field. Oh, and lightning. Each of these effects is accompanied by light. Why? Well, the ionized electron does not remain free. It very rapidly connects to another atom, and it wants to jump to a lower energy state. But because of the law of conservation of energy, that means it's got to get rid of some of that energy, and that energy is gotten rid of as a photon of light, as light energy. So that's why there's a spark associated with it. I have here John Travoltage. So this is what happens on a dry day. If you've ever touched a piece of metal on a dry day and gotten a really big shock, what's really been happening is you've been rubbing electrons off of the floor. I'm going to mute this. There we go. Oh, no, I don't want to mute this. You've been rubbing electrons on the floor, and you're building up your own electric field. Where are the electrons gathering? On the outer edge of you, because like charges. Okay? And then if you make the distance small enough, because it's 3 million volts per meter, if you reduce that distance enough that lightning can jump the gap, bam, you get your shock. Okay? We can also do this mechanically. There's something called a Tesla coil. A Tesla coil basically generates really large voltages and sends out sparks, small pieces of lightning about 30 centimeters long. But if you're clever, you can attach the Tesla coil to a second circuit, and what the second circuit does is it turns the lightning off and on to given frequencies, and you can play music. I should have had this queued up. I have a musical Tesla coil. I purchased it a year ago, and I've been assembling it. The assembly has been a nightmare of epic proportions. And so, in fact, it reached the point after spring break, I've temporarily put it aside. We were almost done. We thought we were doing this over the Christmas break last year, a friend of mine who's techie and myself, and I swear to you, we dropped it, and we felt like such idiots. So a bunch of parts got broken. We had to reorder a bunch of parts. I'm at the point now where it's blowing a fuse, so at least I know electricity is flowing, but I can't figure out why. So my dream, I wish for you, I had a musical Tesla coil. I can only show you one. This is from a kid's science project. So this is a Tesla coil, and he's wired it to a circuit that can turn the Tesla coil on and off with a frequency to play music. I would not want to be in the way of that spark. That's about 1 meter long. That's about 3 million volts. Probably wouldn't kill you, might be enough to burn you. It would sure hurt an awful lot. This is about as good as it gets for a kid at a science fair, because the camera's going to pan around and you're going to see the whole gym is making its way to him. This is nerd heaven. I'm doing science and I'm briefly popular. I'm the cool one right now. You can see he's kind of emptied the gym out towards him. And so literally all the way we're getting sound is the sparks are pulsing in gaps quicker than our ears can pick up, but they're pulsing at the frequency of the music, and our ears translate that into pitch. Okay? So yeah, lightning can also play music. Where do you not want to be in a lightning storm? Pardon me? Why a boat? Could be a wood boat. In particular, what might be more dangerous, I have a sailboat, and we don't get lightning crazy out in the West Coast. On the East Coast, especially in the Florida area, they get spectacular lightning storms. And so every sailor out there, because your metal mast is basically a lightning rod, it's reducing that distance so you no longer need 3 million, you need a smaller voltage to cross that 3 million volts per meter of ionization. And so in Florida, you're always watching the horizon, and especially when it's humid and muggy, because that's when thunderstorms build, and there's one on the horizon, we are getting out of here now. So that would be one area. I totally agree. Where else would be a bad area? Why? Again, it's reducing the distance required for the charge to jump, for the atmosphere to ionize. So I think I said this to you when we brought out the Van de Graaff, but I'll say it to you now, and I'm being very serious. If you're ever hiking on a muggy, cloudy day in the mountains, and you feel like your skin is all staticky, you can feel the hair on your skin standing up, you need to scream loudly at your friends, and this is life or death. We need to get to a lower altitude right now. If that means dropping our backpacks, we're dropping our backpacks. We need to sprint, and we need to get down to 300 or 400 meters lower as fast as possible, because we are very close to the tipping point of the electrostatic force being able to jump the gap. Okay? So yeah, don't want to be there. Where else? Why? Same thing. The tree is able to make this gap shorter. Lightning will hit the tree, but then the current will go down the tree and arc into you or go through the ground. So those are all bad places to be during a lightning storm. How do you survive a lightning strike then? It's a good question. Pause the video. Just a reminder, because I don't think I emphasized it enough. I think it's on the next page for you folks. Is that right? If we know the electric field, I did give you this. This is the definition of electric field. It's the newtons per coulomb. Please be aware that's also another way to find force. Lena, get the F by itself. Times by Q. This is the equivalent of when I gave you gravitational field. I said its definition was that. If I... we're looking for somebody? Hang on one second, please. I'm just recording live. Get the FG by itself. This is how we did the force of gravity last year all the time. That was get the obvious one, right? So, again, I'm trying to reiterate, the mathematics of electric fields are very similar, Wolf, to the mathematics of gravitational fields. Different constants and mass, kilograms, charge, coulombs, but they behave mathematically very, very similarly. The reason I mention that is I think on the Ultimate Review there's a couple of times when they give you a charge at a location and they tell you the electric field of that location, they start asking, find the force. It's meant to be easier, not tougher. Okay? Faraday cage. We've talked a little bit about a Faraday cage. Here's a good example of a Faraday cage. This is from MIT. So we have a Van de Graaff generator. We played with one of those. A grounding rod. And we have a little Ben Franklin doll with tinsel. Why Ben Franklin? He was one. So Benjamin Franklin is unfortunately the person that decided that electrons are negative and protons are positive. He got it wrong, Cohen. There's a running engineering joke. Electrical engineers say, if I build a time machine, the first thing I'm going to do is go back to Ben Franklin and say, no. Call that one positive. He didn't know the difference. He had just two substances. Could you name that substance positive and that substance negative? Because when electrons are negative and you're losing electrons, you have to do the minus thing to get the charge all the time. Just dumb. You got them backwards. Anyways, what's going to happen if we turn on the Van de Graaff generator? Well, charges will leak into the air, and some will gather onto Ben Franklin. Even though he's not touching the Van de Graaff generator, there is still enough so that like charges, see the tin foil, okay? We brought the grounding rod in to discharge it. There's still a little bit of charge left on Ben Franklin, but when he touched it, it went through him into the ground. What happens if we put in a metal cage? And by the way, you can have gaps. That's just fine. So you can breathe through this, no problem. There's our Faraday cage. And the bottom is aluminum foil, so he's surrounded by metal. You can see we're arcing. We're definitely charging up the cage. Can you see the tin foil with Ben Franklin moving at all? Nope. But there's still definitely like charges repelled. Okay. This is also why AM radio will often kick out if you're if you're under a metal bridge where everything is made of metal that acts like a Faraday cage, because that's sending out an electromagnetic wave as well. Behaves like a Faraday cage. How many of you have seen the big power lines, the ones that run over the mountains, the huge metal tower ones? You know the ones I'm talking about? Okay, those extend all across our country, all across the continent. Sometimes they're road accessible. Most of the time they're not. So here's the question. How do they work on them? How do they maintain them? This is one of the more interesting jobs out there. If you're looking for an interesting job, you could try this one.
And empowers this white knight on a quest to keep the juice flowing.
They use helicopters.
I don't give two hoots and a holler about flying inside a helicopter. Outside. That's where I want to be. That's where I want to be. On a magic carpet. On a magic carpet. Back in the late 1800s, a gentleman by the name of Michael Faraday, he enclosed a man in a metal cage and energized that cage, and whatever would still live. The voltage would flow around him.
So what he's doing there is he's bringing himself and the helicopter to the same voltage as the wire. What's another word for voltage? Starts with letter P. He's bringing it to the same potential. And the reason they use the word potential, you might now be able to understand. If two objects are at the same potential, charges won't flow between them. Current won't flow between them. You have to have a potential difference, a difference in voltage. This is why birds can survive landing on a power line. They very quickly get a tiny bit of charge, not enough that they get a shock. They very quickly get to the same voltage potential as the wire, and now they're fine. No current will flow over them or around them. Okay?
I wear a hot suit. 75% fire retardant and 45% stainless steel thread. Metal thread means I have a Faraday cage around a 500,000 volts pass over my body without interference from electricity. As long as the helicopter is isolated from the ground, we are going to bring ourselves to the same voltage potential as the line. Like a bird on a wire. Pilots vary. It's like you can read our every thought. There's such a hunger for electricity. Nobody wants to take lines out of service just to maintain.
So you'd have to be comfortable with heights, Alex.
I've had many people ask me, what do you do? I say, everything that we make is thought of. So it's crossing the street. It's not a job for a hot dog. been afraid of.
I've ever been afraid of.
Electricity, heights,
and women.
and I'm married too.
So a nice application of a Faraday suit. That's a job if you're good at heights, if you're comfortable with heights. I would imagine the pay is fairly good. I would imagine it's also an interesting job. It's never the same thing over and over. You're out in nature. So, Alex, maybe a career for you. No, you want to be staring at your phone, don't you? Uh-huh. Alex, one more. Stay off your phone. I'm going to pause the video.